All right, hey everybody. Welcome to Tuesday morning exam week. Very exciting. Paper up here for you. We'll wait a couple more minutes and make sure everybody gets here who wants to. Hey, Lenny. Hey, Alyssa. Everybody hear me okay? Hey, Jessica. Hey, Renette. Hey, Maria. Morning, Hannah. Hey, Jennifer. Oh, we got a big crowd today. That's great. All right, so as I mentioned, today is going to be focused on getting ready for the exam, making sure that you have what you need in terms of review, answering questions from the homework, things like that. So, to start, I thought we could just take a quick look at kind of how you know what you have to know for the exam. And the best way to do that, oops, sorry, let me change my thing here. There we go. Best way to do that is just to look in Blackboard. And in the learning modules, in each week, we had a set of objectives that you have to that we said were kind of the goals for each unit. So we've got all of that listed throughout here. And if you have any questions about, do I have to know that or do I have to know that? This is a good place to start. So for instance, I had a question on Discord. What specific ions do we have to? Let me make sure I have that wording right. What compounds are the ones we are supposed to memorize? So right here in week 4, you can see that's where we talked about identifying compounds, and clearly it stated, give the name, formula, and charge of the following polyatomic ions: ammonium, carbonate, bicarbonate, hydroxide, nitrate, phosphate, and sulfate. So those are the polyatomic ions that you need to know. There are a whole bunch of other ones that you've probably worked with in the homework. If if there are other ones like that on the exam, I would give you the formula and the charge, or some way of figuring that out. So, hey, Monica. So, that's kind of how you can find out like what types of things you need to know. Um, so that's a good place to start. Remember that that the exam is here, so everything above that is fair game for the exam. I think you'll find it fairly predictable what would be on there. Nothing too unusual considering what we've been doing. But I do want to answer any specific questions you have. So if there are things that you want to go over, if it's specific mastering chemistry problems or other types of things that you're not sure about, examples from the handouts, you can leave those in the chat or on Discord. I've got a few questions here from on the Discord, so I'm going to go through those also. And if you want to join in, please do. Hey, Maria. All right. So first request here, hey Randy, was to look at the last or the most recent handout. And Alyssa also asks for electronegativity for polyatomic ions. Okay, so everybody has some questions about polarity, because that's what this one is about too. Polarity and electronegativity. So let's go through that again. All right, so there's a couple different concepts with regard to polarity that you need to know. So one is just this idea of electronegativity, that some atoms naturally have this property called electronegativity, which means that they tend to attract electron density in a covalent bond. So all of this only matters in covalent bonds. So when you have a bond between two atoms, like H and O, then we can look at that particular bond, look at the difference in electronegativity between those two atoms, and decide if that bond is polar or not. So this only takes place in covalent bonds. So like Alyssa asked about electronegativity for polyatomic ions. So if we had a polyatomic ion like let's say NH4 plus, how could we deal with polarity and electronegativity with that ion? Well, we'd have to first come up with a Lewis structure, which is this. And that whole thing is positive. And there isn't an electronegativity value for the whole thing. There isn't a polarity idea for the whole thing. It's an ion, so it's charged, so it will attract other negatively charged particles. But within the molecule, all we can really talk about is the individual NH bonds. Are they polar? And to figure that out, we go back up to our electronegativity values and we see nitrogen is 3, hydrogen is 2.1, so that's a difference of 0.9. So we would say that those bonds within ammonia are polar. But because of the symmetry of the molecule, and actually the real shape of ammonia, because it's got four things attached, there would be tetrahedral. Like that. And so what ends up, this is really kind of hard to visualize. It actually is easier to think about flat, even though we know that's the real structure. But those polarities end up canceling each other out because all of the electron density is pulled toward the nitrogen evenly. So we don't actually have a positive and negative side on this ion. We have kind of negative in the middle and positive on the outside, and that's not considered polar. So this would be a if we're trying to use these concepts of electronegativity, that's what we would do. We can look at the individual bonds and we can decide if they're polar or not. We can look at the overall molecule and see how that shape works out. But because the overall structure is an ion, it's overall positively charged, this is actually going to behave more like a polar compound in that it's going to dissolve in water. But that's because it's an ion. All ions are compatible with other polar things like water because of the charge. So that overall charge kind of supersedes the structural analysis like we would do. And we generally think about this difference of electronegativity and the polarity. We generally think about that more inside of a neutral molecule like water. So water is a good example, which we looked at somewhere. Because the OH bond is polar, so the oxygen side ends up being more negative, and the hydrogen side ends up being more positive. And so anytime you can kind of draw a line or a plane through the structure and say one side is more negative and one side is more positive, that tells you that that molecule is polar for small molecules like that. So that's what we're trying to do there. Look at the electronegativity and first judge the polarity of an individual covalent bond, and then look at the molecule overall. Other questions about that, or did that answer your question, Alyssa? Does that raise other questions for other people that you want to talk about? Uh, yeah, good question. So Brandy asks, how do you know one side is positive, um, you look at the electronegativity values. So the lower electronegativity is more positive and the higher electronegativity is more negative. And if that difference is more than 0.4, then we say, yes, uh, the more negative, the electrons are pulled toward the value with the higher electronegativity. And so that if the electrons are pulled away from one side, the other side that they're pulled away from is going to be more positive. So in an OH bond, the electrons are pulled toward the oxygen because oxygen has the higher electronegativity. And then so we end up with negative over here and positiveness over here. And again, these aren't full charges like an ion, they're just partial charges. Will you have access to the chart with the electronegativity? Yes, you will have the electronegativity values on the exam. Okay, so we got a couple. I think we've got a couple of questions about molecular shape, but just quickly, I'll answer. Can you use the test printouts with tables of periodic table, electronegativity, metals and nonmetals? So yes and no. So you will. The test itself will contain the printouts that you can use because you can't use your own notes or other writings. So you'll have a periodic table that will include all of the elements, the numbers, but also the names. And you'll have a chart of electronegativities. You won't have metals, nonmetals, or labels for the groups. So you won't have those on those periodic tables. You will have column numbers and things like that, but not specific charges for atoms. And the same thing. So both groups would have access to the same information. Speaking of which, if you're thinking about doing the live exam, I am right after this class. I'm going to record an example with another faculty member, and I'll post it on Blackboard. It's not going to be on YouTube because I didn't want to make it public, but it will be on our Blackboard, so you can see what that exactly is going to look like for those of you considering that. All right, so let's answer these questions about shape and then how that comes into this also. So I have a question on Discord about valence bond theory and about molecular shape, and then this chart, and that kind of goes into this chart on the last page also. So first of all, valence bond theory means a couple different things. So I'm not sure exactly the details of this question, but valence bond theory usually deals with something called hybridization, where we look at how these specific orbitals that the electrons are in combine. We haven't talked about that. That's not something that's on the exam. But a part of valence bond theory is also kind of comes from this idea of what we call VSEPR or molecular shapes, and that will be on the exam. So can you figure out what shape a molecule is going to be based on the concept that electron groups, bonds, and lone pairs push each other out of the way as much as possible. So they always spread out as much as they can. And then, so this kind of stuff will be there. But how those correspond to like specifically where the electrons are, which is valence bond theory. If you see any examples of like hybrid orbitals, sp orbitals, things like that, we haven't done that. So that's certainly not going to be on the exam. All right. So then with molecular shape and with that table on the last page, I guess let's look at this first. So with the table on the last page here, does it contain polar bonds? That is as simple as looking at the Lewis structure and determining the electronegativity differences between atoms. So if you have like CF4, you look at the CF bonds and you say, yes, they're covalent or they're polar. If you have one that is has multiple different types of bonds in it, like let's say CCl2F2, you'd come up with a Lewis structure for that, and same idea. So let's look at that one and work through that one. A little bit more paper. Let's look at this one, and we can look about how to figure out the shape, and then also how that corresponds to the polarity. So first step is always Lewis structure. Let's keep track of that actually. So first, draw the Lewis structure. Then we find the shape, and then we can deal with the polarity. It kind of has to be in order because the previous ones always, or the later ones always depend on the previous ones. So all right, so let's come up with our Lewis structure. CCl2F2, that's going to be 4 electrons for carbon, 7 for each chlorine, and there's 2 of those, and then 7 for each fluorine, and there's 2 of those. So that is a lot of electrons, 32, I think, right? Yeah. So we've got 32 total electrons in this compound. We're going to assume here carbon is the central atom. And I kind of put this down in this shape for now, but you noticed I also could have gone like this. And there's a question of, are those the same or are they different? And it turns out that it kind of depends on the shape. So we'll get into that in a second. I'm going to leave both of those down for now. We have used 8 electrons, so that means we have 24 more. So we can start filling up octets on the outside. And that should, if you see the numbers here, that should work out because we've got 6. We need to add 6 electrons to each of these to get to the octet. And there's 4 atoms, so 6 times 4 is 24, plus 8 is 32. That should be all of our electrons. We shouldn't need to do any multiple bonding or anything like that. Okay. So that's our Lewis structure. This one's going to end up the same way. Remember to check a Lewis structure, make sure it's right. You want to look at, do I have the correct total number of electrons? So do we have 32 electrons? We can count them all up and say, yeah. Then we need to check if everything follows the octet rule, except like hydrogen. So we look at that. So 2, 4, 6, 8, good. 2, 4, 6, 8, good. 2, 4, 6, 8, 2, 4, 6, 8, and then the central carbon 2, 4, 6, 8, because we count the shared electrons for both of the atoms on either side of that bond. So there's our Lewis structure. Okay, now when we figure out the shape, we need to look at how many of these electron groups are around the atom, around the central atom. So how many things, whether those things are atoms or lone pairs of electrons, are connected to that central atom. In this case, for this molecule, there are 4 things connected to the central atom. And so 4 electron groups means that our structure is, our geometry is tetrahedral, and there are no lone pairs, so the shape is also called tetrahedral. Okay, so now to judge the polarity, we may need to redraw this a little bit. And I'm just going to tell you, this is a hard one. This is something I wouldn't probably put on the exam, but let's look at it anyway. So let's draw this in its tetrahedral form. All right. And now, I don't know if you can see this very well, but sometimes it's helpful to think about the geometry here as, let's say, 2 triangles. So if you imagine like a triangle between these 3 atoms, that's a flat triangle. Kind of see that? And then there'd also be a triangle kind of pointed back. So it's almost like 2 triangles meeting at the tip, but like perpendicular to each other. So there's one triangle, and there's another one kind of like under here. And they're perpendicular to each other. So if I were to kind of like move this around a little bit, maybe draw it a little bit differently, it might look something like there's one triangle that's like flat with the screen, and then there's one triangle that's kind of coming out this way perpendicular to it, like that, where like this side is coming out towards you, and that side's going back. So that's the general shape of a tetrahedron. And the reason I talk about that is this actually affects the polarity. So when we want to look at the polarity, the first thing we do is we look at the individual bonds and decide if they're polar and how polar. So we look back up at our electronegativities here, and we see that carbon, oh, I can't see it here, but I know that it's 3. So the difference between carbon and chlorine is 0.5, and the difference between carbon and fluorine is 1.5. So our difference in electronegativity between carbon and chlorine is 0.5, and the difference in electronegativity between carbon and fluorine is 1.5. So what this tells us is that a carbon-fluorine bond is more polar than a carbon-chlorine bond. So the electrons are pulled more toward the fluorine than they are toward the chlorine. And what that tells us then is that this is actually a polar molecule, because the fluorine side is going to get most of the electron density or more of it, and the chlorine side not as much. So the chlorine side is going to be a little bit more positive, and the fluorine side is going to be a little bit more negative. Now that's, again, I said that's difficult because tetrahedral compounds like this are difficult to visualize in three-dimensional, especially 3 dimensions, especially, we don't have models. If we did this in class in person, we would be messing with models and you could actually see that. But we can't do that right here. What I can do is I can rotate this around and redraw it a little bit. Maybe you can see it a little bit better. If I imagine I'm like twisting this around a little bit that way. If I do that, then my chlorines end up over here, and my fluorines end up here. And now you can see that triangle structure a little bit better. Triangle, triangle. And so what I'm saying here is that the negative part is going to be more toward the fluorine because that's more electronegative, and the positive part is over here because those bonds are not as polar. So these are more polar, these are less polar, so the overall molecule will be a little bit polar. That's certainly a tricky one, and that can be really difficult to visualize. Now, if we had a compound with a tetrahedral compound where all of these things were the same, if they were all fluorine or all chlorine, which was the example up here, then you actually end up with a non-polar overall molecule because everything is spaced out evenly and it's not lopsided. So the best way to determine if the overall molecule is polar or non-polar is it symmetric or is one side different from the other? If one side is significantly different from the other, if you can draw a line and say this side is doing this and this side is doing this, that's a good indication that the whole molecule is going to be polar. This is kind of a little bit of a step past the basic objectives, so you won't see really much of this on the exam. You will see like judging bond polarities, but the whole molecule thing, as I mentioned last week, when we get into the really more interesting molecules, the organic molecules, the bigger things, this ends up kind of not mattering so much anyway. So you do need to know the shapes, and you do need to know bond polarities, but if you're stuck on judging the whole molecule's polarity, that's okay. All right, is that helpful for those of you who had those questions? And then what do you want to talk about next? Make sure I got everybody's questions here. The density. Check this here. polarity. Yeah, I mean that's kind of what we were just doing. So let's go back up here where we first started talking about that stuff. And you may want to look back at last week's video too for a little bit more in-depth discussion. But you're going to look at any given bond. Where'd that table go? There it is. So any given bond, so like a NO bond, let's say. If we want to know if that bond is polar, we look at the electronegativities. So N is 3.0 and O is 3.5. We look at the difference in those. The difference is 0.5. And so that means that this is going to be a polar bond. And to determine where the electrons go, well, the electrons are always pulled toward the higher electronegativity. So if it's a difference between 3.0 and 3.5, the oxygen here has the higher electronegativity. So the electrons are being pulled toward the oxygen. So we have to be a little bit careful with that term density, because density is just a very general term, which means how much stuff is in a particular amount of space. So it's not like the density of the object, but more the what's called the electron density, which means the electrons are kind of thicker around the oxygen than around the nitrogen. So the oxygen side gets a little bit negative, and the nitrogen side gets a little bit positive. You may have seen those symbols in the book. That's just a lowercase delta. That means a little bit positive, a little bit negative. Yeah, so let's look at why this is tetrahedral. So first of all, before we get to that, this is really the key part of that, this table here. When you figure out how many electron groups there are, how many things there are connected to that middle atom, that always corresponds with a particular geometry. So if you have 4 groups on the atom, whether those groups are bonds or lone pairs, bonded atoms or lone pairs, that will always be a tetrahedral shape. So it will always take this shape because that's how the electrons can be spaced out from each other as much. At least that's what the theory says. And then, so that's what we call the electron geometry. So going back to that number 19, what I did here was I came up with a Lewis structure, and I recognized, okay, 4 groups, and those 4 groups are going to space out as much as possible, and that leads to a tetrahedral shape. Also, the other interesting thing about that is it also means that these 2 structures are equivalent, and this is another reason why shape is important and not just Lewis structures. If we just draw these as flat structures, they're clearly different. One has the fluorines across and the chlorines across, and the other one has them like this. They're definitely looking different. But in a tetrahedral 3-dimensional compound that we can rotate any which way, those 2 end up being the same. So if you notice, like take a look at this one. If you look at this from like this angle kind of down this way, it looks like the 2 chlorines are on top and bottom, and the fluorines are on left and right. So it kind of looks more like this one. But if you look at it more from the other side, kind of like this, now it looks like the chlorines are on one side and the fluorines are on the other side. So those actually end up being equivalent when we put them into that 3-dimensional shape. Other question, will we be given the formulas for converting Fahrenheit, Celsius, and Kelvin? Yes, you will get those formulas. That's a good example. Let's do that one. OF2. So again, let's look at the Lewis structure first. So we got to figure out the number of electrons, 6 for oxygen, and then 7 for each fluorine. Gives us 20 total electrons. And then we would look at the structure. So O we're going to assume is in the middle. And now we need to add the remainder of our electrons. So we've used 4. We need 16 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that works out. We don't have to put any multiple bonds or anything. And now we have to figure out the shape of this. So it looks like it should be linear because it's got 2 things attached and 2 atoms, want to be spaced out. But this is actually not linear. Can anybody tell why? Why should the structure not be linear even though there's only 2 atoms attached. What else is there that we're not accounting for? Yeah, we have to actually look at all the electron groups, including the atoms, but also the electrons. So this actually has 4 groups here. There's 4 groups on the central atom, not just 2, because the lone pairs, these electrons that aren't bonding on that central atom, still count as electron groups, still push everything away. So we can go back up to that table now and say, okay, we've got 4 groups. That makes it tetrahedral in geometry. So everything's going to be spaced out in tetrahedral geometry with the 2 atoms and the 2 lone pairs of electrons. But since we don't actually see those lone pairs, the actual shape, the molecular shape, we would call bent. All right, so if we were to redraw this, we need to leave space for those electrons. So we could draw it like in a tetrahedral way. Like that, with the other electrons here too. So that there's a spot for each electron group, and we call that the electron geometry, and that's tetrahedral. But then we also have the actual physical shape that we see. Now, the physical shape that we see doesn't include the electrons because we don't actually see them taking up space. So we see this, and that type of a structure is bent. So the electron geometry is tetrahedral, but the molecular shape, oops, not shape, is bent. So it's bent. So you have 2 possible ways of describing the structure. The electron geometry, how everything is laid out, including the electrons, and the shape, which doesn't include the lone pairs. So then Monik asks, Ni3 would be trigonal or tetrahedral. So actually N anything 3, we'll just say X, is always going to have this type of a, that's not quite true. I'll do that. Let's look at that specific example. Are you just telling me to do quiz questions? So then Ni3 ends up being something like this. And so you end up with 1, 2, 3, 4 electron groups. So the electron geometry, we'll call that EG, is tetrahedral. But that molecular shape ends up being trigonal pyramidal. So let's go look at our table again. If we have a tetrahedral electron geometry with 1 lone pair, that lone pair takes up one of the spots, and so the resulting shape is called trigonal pyramidal. So electron geometry tetrahedral, molecular shape trigonal pyramidal. Does that help? Okay, great. What else? Well, you tell me. What do you think? We need a little bit more information. We need to find out, is an Ni bond polar or nonpolar? So nitrogen here is a 3.0, and iodine is 2.5. So those bonds are polar. And if we look at that trigonal pyramidal shape, yeah, you'd have the electrons being pulled toward the nitrogen away from the iodine. So the nitrogen would be a little bit more negative on top, if you imagine the pyramid being the nitrogen on top. And the iodine would be a little bit more positive. So you'd have more of a negative side on top and a positive side on the bottom. So hopefully also here, having done some of these and looked at these, you're starting to see some patterns. Atoms tend to bond in these structures in fairly common patterns. So like notice that almost every n something 3 structure that we've looked at has had the same Lewis structure, the same geometry, all of that stuff. Um, so you can use those ideas when you're doing your quizzes and exams to think like to check your answer and say, does this look right? Does this seem like a reasonable nitrogen structure if it's a nitrogen structure, for example? So this asks, how does the lone pair of Ni3 factor into the polarity of the molecule? It doesn't. It doesn't accept that it changes the shape, and that affects the polarity. But the polarity is only based on the atoms and the shape of the molecule. We don't include the lone pairs as pulling or remember polarity is only an aspect of a covalent bond. So you have to have a covalent bond between two atoms where the electrons are being pulled to one side more than the other. That's how we have a polar bond. So if we don't have that, then we can't. Then there's no polarity. So the lone pairs don't contribute to the polarity. They only contribute in the way that they change the shape, and that that affects it. All right. What else? Here? Well, while you're thinking and waiting, I want to look at a couple of the mastering chemistry questions that were. I think I can. I think I can see which questions were the most widely missed, so we can look at those. Anything else you want to look at? Please enter it in. Okay, yeah. So it's kind of this general one here. I'm gonna copy this over in the notes here so you can see it. So it was this one where it had these two kind of generic atoms, X and Y, with their Lewis structures shown, and it said, what are the group numbers? Would you expect it to be ionic or molecular? Which ions would be formed? And what would a formula for that compound be? So let's figure out how we could do that. So first, remember that the reason that this works, the reason that you can actually do this, is that Lewis structures tell us the number of valence electrons, and the number of valence electrons corresponds to the place on the periodic table. So we would say that X has one valence electron, and Y has 6. So then if we look at our periodic table, we would say, okay, well, the atoms with one valence electron are the ones way over on the left. So the alkali metals, hydrogen, lithium, sodium, potassium, rubidium, cesium, and the compounds or the atoms with six valence electrons tend to be the neutral ones anyway tend to be right here in column 6A. So oxygen, sulfur, all of that kind of stuff. So we could say this is likely to be in 1A and this is likely to be in 6A. And then that can give us some clue as to how they might behave. So if we would imagine, should it be ionic or molecular? Well, if we're saying this should be in column 1A, we're really saying that's a metal, right? The only exception being is if we thought maybe it was hydrogen. So we're guessing, but it's more likely to be a metal. And this one in 6A is more likely to be a nonmetal, so that combination we're guessing is probably ionic. In terms of which ions are formed, ions can be formed by either gaining or losing electrons. The more common ions are for either are for the fewer number being lost or gained. So we would expect an atom with one electron to lose that electron and become X plus. And we would expect an atom with six electrons to gain two electrons. So this would be minus an electron, and this would be plus an electron. Plus two electrons. So to gain two electrons and become, so it has a full octet, and if it gains two electrons, now that becomes 2 minus. So we're expecting here a compound or an atom that is plus 1 and an atom that is minus 2. So then that compound being put together is going to look something like X2Y. And a specific example of that would be something like potassium and oxygen, or whatever, rubidium and sulfur, anything between those two categories. But this was just, I think it just threw people off because it wasn't a specific example. It was saying just in general for a generic example. All right, other questions? Yeah. Will you have the table with the valence electrons? What do you mean the table with the valence electrons? Oh, you mean like where there's actually a picture of all the Lewis structures of all the atoms? No. You can find the valence electrons from the position on the periodic table. So you'll have a periodic table like this, and from that you can find the valence electrons from the columns, and you can go back and review how to do that. But for everything except this middle transition stuff, which we just are kind of we don't talk about Lewis structures with those. They mostly make ionic compounds anyway, the ones that we'll see anyway. But for column 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A, the number of valence electrons is just the column number there. So you can find it from the periodic table. Okay. So another one, and this kind of goes with what we were practicing earlier with the shape. Another one from Mastering Chemistry that was missed pretty widely. This one. Yeah, I'll go back to the nomenclature in a second. Let me finish this one and then we'll look at that. So we've got, it said, what is the shape around the orange colored atoms, which here are carbon and nitrogen. So again, there's nothing tricky about this. It's the same as any other find the shape thing. The only issue is it's a bigger molecule, so you have to look at each individual atom. So we don't say what is the shape of this entire thing, because there's just a bunch of atoms. It's a whole mess of shapes. But we can look at each individual atom and the shape within there. So we can say, if we're only looking at this carbon, what's the shape? Sorry, this this carbon right here. And we do it the same way. So we look at 4 groups there, and we'd say that's tetrahedral, electron geometry, tetrahedral shape, also molecular shape. Then we'd look at the nitrogen separately and say, okay, this nitrogen has 4 groups, making it a tetrahedral electron geometry and a trigonal pyramidal molecular shape. And we could do the same thing for this carbon too. So in larger molecules like this, you look at each interior atom to determine the shape of that particular atom. Pull back up the naming rules. So now that we've kind of gone through this, let's return to this flow chart that at first was kind of unwieldy and may still be unwieldy, but now that we've actually looked at all the names, let's see if we can navigate through this a little bit and make it make some sense. And maybe the answer is no, and that's okay. You don't have to use this flow chart. If you find it more confusing, just do it however you're doing it that works. But the thing I like about the flow chart is it makes it clear that you have to make particular decisions in order to get the correct names when you're trying to name these compounds. So first you have to decide, is this an ionic compound, a molecular compound, or an acid? If you get that wrong, if you don't make that decision correctly, then you're going to always end up at the wrong name. All right, so let's review how we find those. Acids are always going to start with H. That's probably the easiest. And there's usually going to be some, not a whole lot after that. So just H and then, some ions or something else. Molecular compound, only nonmetals in this case. We also call this a covalent compound because some of these are not molecules. So when you only have nonmetals. Then we also had the ionic compounds, where you had a metal and a nonmetal. Now, the exception here, which we should also note, the only exception that we are going to see in this class, whoa, button here, is also NH4. If we have, what? Okay, somehow I changed my pen here. Sure how I did that. But anyway, if we have an NH4 ion, you could have a compound that is totally nonmetals and is still ionic. So like NH4 NO3 or something like that. Okay. So let's say we decided it was molecular, then that's just the basic molecular name. So, you say the prefixes diphosphorus pentoxide or whatever, and that's it. That's probably the easiest one. And that's also where people mostly get tripped up, is because they want to name everything like a covalent compound, whereas the ionic compounds have different rules. So you can't just say di, tri, whatever for anything. It has to be a covalent compound. If it's an ion, we have to use the ionic nomenclature, and then we have to make another decision. I'm going to delete these because that was from another thing. The decision we have to make next is, does this form only one type of ion, or does it form more than one type of ion? So one type of ion means it's always +1 or always +2. So column 1, column 2, and aluminum. There's a couple more that we said don't worry about. Everything else kind of in the middle makes more than one type of ion. So that's your next decision. And then once you've made that decision, you can name based on just the metal and the anion, if it is only one type of ion, or you can put the charge of the cation in parentheses if it's something that makes multiple ions. So that is kind of the quick review of that side. Over on the acid side, there's 2 ways to name acids. It can either just be hydrogen and one other thing that's binary. So that's your hydro something acid, hydrochloric, hydrobromic, hydroiodic. Or there are the oxyacids that contain oxygen, where you use the entire ion's name and don't put hydro in front. So phosphoric acid, sulfuric acid, sulfurous acid, stuff like that. I will only test you on the more common of those, so names and acids that you've almost certainly heard before, based on the ions that you need to know. So I won't throw these like sulfurous acid from sulfite, because sulfite isn't an ion that I am expecting you to know. You can expect most of the naming to be in this realm over here. Okay. Well, other questions before we go? Yep, no problem. All right, is that I guess that's it. I haven't heard anything from anybody else. There's nothing else going on in Discord, so send me notes if you have other questions. Review this stuff. Review everything else. The um, the exam. So the quizzes are due tomorrow, and the exam will pop up then on Thursday, because I want to make sure everybody does those quizzes first. If you're planning on the Mastering Chemistry with Honor Lock exam, that you'll have all anytime over the weekend to do that. I would say do it sooner rather than later, just because in case you have technical difficulties or something, then there's time to figure that out. If you want to do an exam with me, please sign up with that through that link that I gave you, and watch for after this class. I will post an example so you can see what that's going to look like. All right, well, have a good day, everybody, and I'll see half of you tomorrow, and maybe more of you online for exams. So happy studying. Thanks. Bye. Thanks, everybody. Bye.